Hello. So, as promised, here's a follow-up to I did the sort of round one on method of undetermined coefficients, where the right-hand sides were pretty nice, right? It was just x in the one case, so we guessed ax plus b. The right-hand side was cosine of x in another case, so we guessed a cosine plus b sine, right? I wanted to show some where they're a little messier, a little more complicated to set up your guesses. So that's what I have here is I have a table of good strategies, how to set up your guess when using method of undetermined coefficients. There's no universal strategy that tells you in general how to set up the perfect guess for method of undetermined coefficients. It's a lot of ad hoc case by case. It's almost like finding an antiderivative, right? In some ways it literally is finding an antiderivative, but it's a lot of, sometimes you'll try a guess and it just doesn't work. You try to solve for the coefficients, you get 0 equals 0 or you get 0 equals 1, right? And so then you try a different guess, to kind of like antiderivatives. Your first attempt doesn't always work, but these are some good guesses, right? If you see a degree n polynomial on the right hand side, guess a degree n polynomial. If you see a sine or a cosine, guess a linear combination of sines and cosines with the same period. If you see an exponential, right, guess that exponential with the same power, but give it an arbitrary constant out front. If you see a product of exponentials and cosines and sines, treat it kind of like the sine and cosine case, but with an e tacked out front. So these are some common cases. They all come with one sort of complicated caveat, though. So I have this sort of maybe a little bit cryptic note at the bottom. If the standard guess would overlap with y sub h, the homogeneous solution, then multiply by x until it doesn't, right? Meaning doesn't overlap any longer, right? I'll show you in an example. This is probably easiest to see an example what I mean here. Let's look at a particular example where the standard guess, and when I say standard, I mean what's up in the table, will overlap with the homogeneous solution. So for example, let's look at second order equation. Right, so I have y double prime minus 6y prime plus 8y. And then on the right hand side, I'm going to have this. I'm going to have we have 2 plus e to the minus 4x on the right hand side. So this is our non-homogeneous linear equation, differential equation that we're trying to solve. So what would we do here by the method from the last video? Well, we recognize that it's, right, we note that the DE is non-homogeneous, but it's linear, right? And well, in some sense, non-homogeneous isn't even defined if it's non-linear, but it's linear and it's non-homogeneous. And we have our theorem that says that the general solution is going to be a particular solution plus the associated homogeneous solution, right? And how do we find each? Particular, we do muck, and the homogeneous, we do characteristic equation, right? So let's start with the characteristic equation. With the characteristic equation, lambda, right, lambda double prime, lambda squared minus 6 lambda plus 8 equals 0. Right, this becomes lambda minus 2, lambda minus 4 equals 0. So lambda is 2 or lambda is 4, right? So I get solutions e to the 2x and e to the 4x are solutions, right? And therefore I have my superposition gives me my homogeneous solution. So there's my y sub h. So I found my y sub h. And sorry, I'm realizing just now. Get rid of the minus in the original equation statement. Right. So this one here, I didn't want e to the minus 4x, just e to the 4x, not e to the minus 4x. So blast that one. There we go. Now it's correct. Right. So I want the right hand side to be 2 plus e to the 4x is the idea. Okay. So we found the y sub h. We found the homogeneous by superposition characteristic equation. Right. Now from here, I now want to get my particular. For y sub p, right? So now, what do I want for y sub p? Look at the right-hand side. The right-hand side has 2 plus e to the 4x in it, right? So the right-hand side has 2 and an e to the 4x. So what is 2? 2 is a degree 0 polynomial. So what does that tell me to do? Look up at the table. If you see a degree n polynomial, guess a degree n polynomial. So I'm going to get, that's what I'm going to do here. I'm going to guess a degree 0 polynomial. So a, just a constant a, just like that, right? So that's for coming from the 2. It's the guess corresponding to the 2. Now, what other terms do I need? I also need something for this e to the 4x, right? So here I see an e to the 4x. So this would tell me to guess what? It would tell me to guess a term that looks like e to the 4x. But here's the problem. This already lies in the homogeneous solution. And why is that a bad thing? Well, it's a bad thing because if I guess e to the 4x in my particular, it's just going to go to 0 when I plug it into the differential equation. Because look at the homogeneous, the associated homogeneous, or the characteristic equation, right? It's solving the associated homogeneous equation. What's the associated homogeneous equation? It's the same equation, but there's a 0 on the right-hand side. So if you plug in anything from the homogeneous solution, it's just going to become 0. That's what the homogeneous solution is. It's the solution set to the same differential equation, but just that has a 0 on the right-hand side. So it's not going to give us that e to the 4x if we just plug in constant times e to the 4x, because constant times e to the 4x is already in the homogeneous. So instead, what do? You guess x e to the 4x, right? And so that's what I mean up here. You want to multiply by x until it doesn't any longer overlap. With the homogeneous, right? So x e to the 4x, that will be a good guess. So that's this phrase up here, right? Where I say the standard guess would have overlapped with the homogeneous, so multiply by x until it doesn't, right? That's what we just did here. So this is going to be my guess for y sub p. A plus bx e to the 4x. Now that I have that guess, now I can plug it. So now plug in for y. and solve for A and B. All right, so what does the DE become? Well, the DE was y double prime minus 6y prime plus 8y, I believe. Right, was that correct? Y double prime minus 6y prime plus 8y. Yeah, there we go. All right, so if this equals what? Well, I want the second derivative, right? Okay, well, I'm going to need the product rule here, right? This isn't a super easy derivative because I have x times e to the 4x. So let's do this. Let's do this carefully, right? Let's actually calculate the first and second derivative before we start plugging in, right? So let's do our derivatives off on the side here to that we have them ready for when we plug in. So what's yp prime? Well, it's going to be the a goes away, right? It'll be b e to the 4x plus 4b x e to the 4x. Right, that's our yp prime. Product rule on that second term. Then I'm going to do it again. I'm going to get b e to the 4x times 4 because of a chain rule. So that's that first derivative, or the derivative of that first term. And then I'll do product rule again here. And what do I get? I'll get 4b e to the 4x plus 16b x e to the 4x by product rule. And so now I have my derivatives. Note I could even combine terms a little bit there. This 4b and 4b is 8b, right? So now I'm ready to plug in. So I have 8b e to the 4x plus 16b x e to the 4x. There's for y double prime, right? Then I have minus 6 times y prime. And y prime here is b e to the 4x minus 4bx e to the 4x. Then lastly, I'll have 8y and y is just yp, right? A plus bx e to the 4x. So there we go. There's our guess, our fancy guess plugged in. We differentiated it right now twice, plugged it in into that differential equation. So now we can unpack all this, right? And if you notice, at the end of the day, we have 3 types of terms. So I'm going to sort it into buckets based on which type of term. So we're going to have constants. We're going to have e powers. Right, so here I'll write them as e powers, right? So e to the 4x. And then we'll have x e powers, right? So x e to the 4x. Those are the 3 types of terms that we have here. So constants, all we have is 8a. That's the only constant around. Right? Now, for e powers, we have what? Well, in the first equation, we have 8b as our coefficient on the e power. In the second equation, we have negative 6b as our coefficient on the e power. Then we have these xe powers. And what do we have there? We have in the first, I have a 16b. On the second, I have positive, positive. Oh, I miscopied a minus sign there. Yeah, this should be positive right there. Positive. There we go. On the second, right, it's positive inside the parentheses. Then when I multiply the 6 through, it's going to become negative, right? Then I have negative 24b. And then on this last one, I have plus 8b. Those are the x times e powers. All right. So then, how does that clean up? 8a plus 2b e to the 4x, right? And this is actually 0x e to the 4x. Okay, that's actually really good, right? If that term didn't zero out, we'd have no hope of solving this. We would get no solution because look at what's on the right-hand side. We're trying to get 2 plus e to the 4x, right? So, well, I shouldn't say it's guaranteed that there's no solution, but that coefficient would have to be 0, whatever was sitting in front of that, right? And in this case, if the b was 0, then we're not going to get that e to the 4x because b is the coefficient there. So yeah, there wouldn't be any e in it at all. So so this one vanishes, right? So now I can say, what is this equal to? It's equal to our right-hand side, right? And our right-hand side is 2 plus e to the 4x, right? So this has to equal 2 plus e to the 4x. So now again, you can equate matching coefficients. This tells me two things, right? 8a has to equal 2. So a is 1/4. And 2b has to equal what? Well, the 1 that I didn't write there, right? So b has to equal 1/2. And now we have it. Now we have our solution, right? So y particular then is what? A plus bx e to the 4x. So it's a plus b x e to the 4x. And we now even know our general. Right, the general solution to the whole differential equation now, remember, is yp plus yh. Well, we have all the information now, right? So it's a 4th plus 1/2 x e to the 4x plus, let's do now y sub h. Where was that? Y sub h. Here we go, where we did superposition. C1 e to the 2x plus C2 e to the 4x. There we go. Where C1 and C2, again, can be any real numbers, right? So this is our general solution to that D, right? So there we go. There's our next, showing off a more complicated example, right? This is either good guidelines in general for how to pick, what you see in the right-hand side. You see a term that looks like something in particular, replace it by these general forms on the right column here. But you might find some overlap between y sub h and the standard guess. So then you just multiply by x and try again, right? And that's what worked here, right? It would not have worked had we guessed e to the 4x. It would have just zeroed out, and there would have been nothing to solve for because it was in the homogeneous. That's what it means to be in the homogeneous. But instead, we did x e to the 4x instead of just e to the 4x. And that's what made it work, right? That multiplication by x. So yeah, so there we go. There's just showcasing a little bit more complicated use of this technique. Right, it's still solving a nonlinear, just like in the last video, solving a nonlinear, a non-homogeneous linear differential equation. And it's still using particular plus homogeneous. It's still using method of undetermined coefficients to find the particular, still using characteristic polynomial to find the homogeneous. So all of that is the same, but it's just quite a bit trickier to set up the guess for the particular. So, all right, thanks. I hope that made it illuminated muck a little bit more.